Uncertainty about future event is the key feature of the world we live in. Uncertainty plays a big role in many business decisions. Operations is often about making good decisions um, in the presence of such uncertain settings. First, I'm going to introduce you to one of the most central problems in operations, a problem of matching demand with supply in uncertain settings called a news vendor problem. To get there, we need to be able to describe uncertainty in our data in order to make better decisions. Hence, we are going to grow our methods to forecast future outcomes. We are going to learn how to think about forecasting when there is a strand or seasonal variation. The descriptive analytics that we already covered, we will build on it and will provide a strong conceptual basis for predictive and prescriptive analytics, especially for operations. To evaluate different courses of action, to optimize and to choose the best possible action, we need to we need to understand this news vendor problem slightly better. And not only this, we have to better our forecasting tools. Okay. In the first series of videos, I'm going to cover 4 topics. Here's how we're going to split it. In the first session, I'm going to talk about operational decision, problem called news vendor problem. After that, after I introduce this news vendor problem, I'm going to talk about random variables, and I'm going to talk about demand distributions, and that leads us to session 2. In session 2, I'm going to talk about forecasting using the past historical data. Now, this is slightly different than the regression. In regression, there was some root cause that we used to make regression models. This time series models are very similar in the sense they use the same mathematical technique, but we use the historical data of the same variable, and this is what we call time series data. We'll talk about moving averages, then we'll talk about exponential smoothing, and in the advanced material, we'll dig deeper into this exponential smoothing. In session 3, I'm going to talk about forecasting when the data shows trend or seasonality. Finally, in session 4, I'm going to talk about forecasting for new products and about fitting demand distributions. Okay. Now let's jump right into session 1, where I'm going to talk about this interesting operational decision problem. Before we dive into analyzing data, let's look at this fundamental problems that firms face. It's an operations problem on how much to produce. To answer this question, we need to know or estimate the cost of the product, the price of the product, right? How much we can sell it for. Some data on the demand of the product. Let's explore this problem to get started. Okay. Suppose you're making an operations decision for a retailer who orders a product from a supplier and sells it to customers. The ordered product items are received and placed in a store shelf. Suppose there is a large consumer population, and each consumer in the population may choose to buy or not to buy the product. If the consumer chooses to buy, or if the customer chooses to buy, he arrives at the store and buys the product. He buys it as long as it's available on the shelf. However, you have to order the product before you see the consumer demand, since you have to have the items available on the shelf. Right? Suppose that you only get one chance to order. That is, you cannot really change your purchase order after you make your decision. Okay? Everybody got that? All right. Let's look at the cost in our operations problem. You order the product from the supplier at some cost. Let's say instead of dollars, let me use the word tailors. Tailors, just like dollars, or some currency. So 3 tailors per item. Tailors are just some currency units that we're going to use in this example. After you order, your order is received and placed on the shelf. some demand, of course, will swap, right? The product on the shelf sells at price, say, $12 an item. All unsold items at the end of the season or at the end of the day are salvaged. You get no money for salvaging. That is, your salvage value is $0 per item. You lose all the money if you buy and don't sell it. Okay. Now let's look at the timeline of the events to understand the problem better. Here's a timeline of events. That is what happens in every period. You submit an order to your supplier, and the cost of purchase is then, say, $3 an item. That's what we decided earlier. You receive all the other items, so whatever you order, you'll receive it. You receive these items, say, immediately or after a week, doesn't really matter. Right? Very small time window passes and before you receive them. And you store them on your shelf immediately. Once you shelf it, there are some unanswered questions in demand. Customers choose to come to the store, and as they come, they see the items on the shelf and they buy it as long as it's available. Let's say the selling price is $12 an item. And the key factor here is demand is uncertain. So you really do not know how many customers are exactly going to show up to the store and buy your item. If you sell all the items that you have bought, good. But sometimes, if you have leftover items that remain unsold, they're going to have to be salvaged. In this example, we assume that the salvage value is $0 an item. So whatever is left is given away or have to be discarded, and you lose all the money, and that's it. The problem ends, and the next period you have to make an order and meet the demand in the next period, so on and so forth. Let's focus on the important point I mentioned before. The demand is uncertain. That is, demand could be anything. It could be high, it could be low, and so on. Suppose you bought 10 items. Let us look at a high demand scenario. Let us suppose the demand is 100. You will sell all 10 items. Even though the demand was 100, you could sell only 10 because that's all you got. You sell all 10 items and make a profit on those 10 items, say 10 times 12 minus 3. You bought it at 3 and you sold it at 12. So that is 10 times 12 minus 3 is $90, right? That's your profit. Even though your demand was 100, you sold only 10, and that's the profit you made. There's also low demand scenario, a demand scenario where suppose there was no demand. In that case, you bought 10 items and your demand is nothing. You sell nothing and you lose all the money in buying those items because you bought them for 3 tellers, 10 items, therefore you lose 30 tellers. This is because there was no salvage value for the items that are left over. With this timeline in mind, let's look at the problem. Based on the information before, let's recap it. To recap, you don't know what the demand is going to be. You have to decide the number of units to order from your supplier before seeing the customer demand. In this case, what could help? Past demand data would be helpful. Fortunately, we have demand data from the last 100 periods. Here's the past demand information. In the graph that you see, you'll see demands that were observed in the last 100 periods. As you can notice, there's a lot of variability in the demand. In the first period of the observation, you see the demand was 29, just below 30. In the last period of the observation, you see it was 41, right? Let's understand the demand part more. Here's some more information about the past demand data. From the observation over past 100 periods, you see that the maximum demand was 81, right? Somewhere here after 40. And the minimum demand was 15, somewhere here again, right after 40. You can even calculate the arithmetic mean or arithmetic average of those 100 observations, and which is, I calculated it for you, it's 52.8. Based on the data, I'm going to ask you to go through one exercise, an exercise in deciding how much you would order. Before you make a decision, There's no penalty for it, that you don't get extra credits. Just think about this. Without knowing anything, having any tool, what would you do? When I teach this class, this topic in a face-to-face class, I make people, take a piece of paper, a post-it note, and write how much would they order. Only information you know is if you order one item and if you sell it, you make $9. If you don't sell it, you lose $3, and this is your average demand and so forth. Okay. All right. Choose a quantity Q that you'll order. Once you select that Q, the market will produce 50 random instances from the distribution of demand that I've shown you. Each random demand instance will correspond to the demand value you may face in the coming selling season. Your objective is to select a Q to maximize total profit, and you will earn when faced with those 50 random values. Right? And this is exactly what news vendor problem is. Let me characterize this even more. So the objective usually is to maximize profit, minimize cost, or to improve market share, but you only have to make one decision. Usually how much to buy, or how much to plan for, and this happens before you see the future demand. Then demand occurs and profits and costs are realized. This is news vendor problem. Right? It is called news vendor because it is similar to a vendor who sells newspapers. You buy too much, you may be left with unsold newspapers. You buy too little, then you'll forego revenue opportunity. Right? If we are doing the experiment, earlier I mentioned where you come up with a queue and then we give you 50 instances, then we would figure out, depending on what that random value is, we could calculate how much money you made or how much money you lost. Okay? Now I'm going to give you an example of this news vendor problem, at a Time magazine, a real story. In the Time magazine's supply chain, they had the following problem. The stores were either selling out inventories, which means they had too little inventory, or they sold only a very small fraction of the allocation, which means they had too much inventory. So this is a news vendor problem. The Time magazine evaluated and adjusted for every issue they printed. The following. The national print order, which is the total number of copies printed and shipped. Second, the wholesale allotment structure, which is how those copies were allocated to different wholesalers. Third, the store distribution, which is the final distribution of the magazines to the stores. Note, the above three decisions were made before the actual demand for the weekly issue is realized. Therefore, they need to analyze the past data and they have to be able to forecast future demand. In fact, Time magazine reports saving about 3.5 million annually tackling this news vendor problem. This story is mentioned in a white paper by Koskat in Interfaces magazine in the year 2003, volume 33. Other than the Time magazine's news vendor example, let's look at some broader applications of the news vendor. Here are some of them. Every year, governments order flu vaccines before the flu season begins. And they make this decision before the extent or the nature of the flu strain is known. One question is, how many vaccines to order? This is a news vendor problem because you have to know how to make your decision before the demand is known. Smartphone users buy mobile data plans before they know their actual future uses. In this case, what's the right plan for you? This is a news vendor problem again because you have to make a decision before future demand is known. Consumers buy healthcare insurance plans before they know their actual health expenditures. This is also a news vendor problem. For all type of examples that we saw, some forecast or future demand is essential. Let's think about how to do this. It's essential to forecast future demand. Right? So let's understand what forecasting is all about. Forecasting, the primary function of forecasting is to predict the future. Why are we interested in predicting the future? Because it dictates the kind of decision we make today. If we know something about the future, we can make better decisions today. Who uses forecasting in their jobs? A lot of jobs use forecasting. Typically, generally speaking, we forecast demand for products. We forecast demand for services. We forecast inventory needs. We forecast capacity needs daily, and so on and so forth. But what makes a good forecast? First, forecast um, must be timely. It should be reliable and it should be accurate as possible. It should be in meaningful units. And then the forecasting method should be easy to use and be understood in practice. Let's look at the characteristics of forecast. Okay? Point forecasts are usually wrong. In fact, this is the first rule of forecasting. Why? Let me give you an example. Let me give you a couple of examples. I forecast that in December 2015, there will be 37 centimeters of snow. Suppose I forecast we will sell 314 umbrellas during next week. Really likely, this forecast will turn out to be wrong. For example, you could have 37.5 centimeters of snow in December, or you could sell 317 umbrellas during the rains next week, or we could even deviate more. This happens because the demand could be a random variable. It could deviate from your forecast, therefore a good forecast should be more than a single number. Typically, we provide a mean and a standard deviation. You could also provide a range, right? High or low, for example. For example, TV weather forecasts provide a high temperature tomorrow and a low temperature tomorrow. That's a way of providing more than a single number. We have to think about modeling uncertain future. Usually, we can model future probability through probability distributions. Let's think about this further. We often do not control purchasing behavior. As a result, we cannot predict future demand with certainty. So how do we describe an uncertain future demand? We can try to decide what future demand scenarios are possible for each scenario, estimate the likelihood of its realization. So where do scenarios come from? Right? Where do scenarios come from? They could come from past data, or they could come from expert estimates. Let's look at an example of a model of future demand. Let's start by looking at a small number of scenarios. Let's say 3 scenarios. Let's call them high demand scenario, ordinary demand scenario, and low demand scenario. Let's say that high demand scenario corresponds to a demand value of 80, ordinary demand scenario to the value of 50, and a low demand scenario to a value of 20. For each scenario, a likelihood of its occurring must be estimated. In our example of model of future demand, we have to estimate how likely each scenario is. Where do estimates of the likelihood come from? Again, they come from statistical analysis of past data. Suppose that after analyzing the past data and using some subjective inputs, we estimated that the scenarios have the following likelihood of being realized in the next selling season. Likelihood of high demand is 20%, likelihood of normal or ordinary demand is 70%, likelihood of low demand is 10%. In our scenario analysis, the projection of the demand is not equal to a certain number with a sure probability of 1, but rather can take 3 values with the corresponding probabilities. In essence, we have created a probability distribution for the future demand. Demand could be 80 with a probability P1 of 0.2. Demand could be 50 with a probability P2 of 0.7. Demand could be 20 with a probability P3 of 0.1. Probability distributions like the one I have described with a number of distinct scenarios, each with attached probabilities. These are called discrete probability distributions. Finally, note that this each of these probabilities is greater than 0 and sum up to be 1. Right? 0.2 plus 0.7, 0.1 plus 0.1 is equal to 1. Okay? In this graph, I plotted how the probability distribution looks like. The scenarios are shown on the x-axis, 20, 50, and 80, and the corresponding probabilities are shown on the y-axis. Probability distributions are typically described by mean and standard deviation. For any probability distribution, even a simple one reflecting 3 demand scenarios, which we just saw, 2 useful descriptive quantities are often calculated: mean, sometimes called the expected value, and the standard deviation. Let's try and describe them. For a discrete probability distribution, the mean is just defined as the sum of the products of scenario values and their probabilities. Let me say it again. It's defined as the sum of the products of scenario values and their probabilities. For a demand distribution, earlier represented by D bar, okay, will be P1 times D1, the probability of 1, the value of demand 1, plus probability of 2, value of demand 2, probability of demand 3, and the value of demand 3. In our case, it is 0.2 times 80 plus 0.7 times 50 plus 0.1 times 20, which comes out to be 53. How do we interpret this mean of 53? It reflects the demand value we'll get on average in the selling season. If you keep observing the deviations over and over and over for infinite number of time, you will get this 53. Right? If you keep drawing observations over infinite selling seasons, the average value or expectation should be 53. Okay? It's the same graph I showed you earlier. The red vertical line represents the mean or expected value of the distribution. Now we'll look at the standard deviation. Standard deviation, roughly speaking, describes how far away the actual random values are, right, from the mean on average. Right? In other words, in the colloquial sense, it describes how spread out your distribution is around its mean. How can you calculate the standard deviation in this kind of scenario? Standard deviation is defined as the square root of the sum of the following things: products of the scenario probabilities, with the squares of the difference between the scenario value and the mean value. Let me say this again. You take the scenario value and the mean value, take the difference, square the difference, multiply it with the scenario probabilities. Right? Do this for every scenario and you add them up. Now then you can take the square root. For example, in our 3 scenario demand probability we consider, the standard deviation is calculated as follows. Take the difference between the mean scenario and the average. Right, the average. Square that. Multiply it with the probability and do this for every scenario. Take the scenario demand, its difference with the average, square that and multiply it by the corresponding probability and do this for every scenario. So you get 0.2 times 20 minus 53 squared, 0.7 times 50 minus 53 squared plus 0.1 times 80 minus 53 squared. And that comes out to be 16.16. Now I'll show you roughly what the standard deviation looks like. The standard deviation is a measure of how spread out, right? It measures how spread out your distribution is around the mean. The knowledge of mean and standard deviation values helps us to support a general intuition about the nature of the random variable. What if we have more than 3 scenarios? It is somewhat straightforward to do this. So let's think about the following scenario. Demand 1 with probability 1, demand 2 with probability 2, demand 3 with probability 3, demand n with probability Pn, and so forth. So we have all the probabilities, all are positive, and they all add up to be 1. Again, each one of this, P1, P2, P3, Pn, all has to be positive, more than 0, and they have to all add up to be 1. Okay. Now, how do we calculate the mean and the standard deviation of this? It's again straightforward, the extension of the 3 case scenarios. To get the mean, right, or d bar, we do P1 times D1 plus P2 times D2 plus P3 times D3 plus Pn times Dn. For a standard deviation, we calculate the difference between D1 and D bar, square it, multiply with P1 plus the difference between D2 and D bar, square it, multiply with P2 plus difference between Dn and D bar, square it, and multiply with P1, right? And take this, add this all up, right? And take the square root of the entire sum, and that gives you the standard deviation. So far, we have looked at the discrete probability distribution with a number of future scenarios. Each scenario with some attached probability attached to it. But what will happen to the discrete probability picture when the random variable being modeled has a really large number of scenarios on very small interval of values, and the probability that one scenario is realized is really small? Think of examples such as stock prices or the amount of rainfall in a region, for example. There are many possibilities in every scenario of very many scenarios of rainfall happening between 37 centimeters to 39 centimeters. And the probability of rainfall being exactly to one scenario, let's say 37.1 centimeter, is really low. In the case like this, it makes sense to describe such probability distributions using groups of scenarios rather than focusing on each individual scenario. Distribution like this is called continuous distributions. In the picture here, I show you the distribution of a random variable x. The value of x are on the x-axis and the corresponding probability on the y-axis. Distributions like this are called continuous distributions. In the continuous distribution case, we're going to look at a group of scenarios rather than a single scenario. Again, the light green area shows you the probability that a random variable x takes a value between a minimum of x1 and a maximum of x2. And the area under the entire curve is equal to 1. If I ask you what's the probability that the random variable x can take any value between the lowest possible point and the highest possible point, the probability must be equal to 1. And therefore the area under the entire curve is equal to 1. One of the most popular examples of continuous probability is the normal distribution. Normal distribution allows for random variable x to take any value from negative infinity to positive infinity, as you see in the graph. The nice thing about normal distribution is it's completely characterized by two parameters: the mean mu and the standard deviation sigma. Normal distribution looks like a bell curve, and it's likely the most commonly encountered distribution. There exist statistical formulas also implemented in Excel that calculate a probability that a normal random variable with a given mu, mean, and a given standard deviation sigma will produce a value between x minimum and x maximum in this interval. And this can be calculated in Excel very easily, and we have done this before. Other than normal distribution, there exist large number of other continuous distributions, exponential distributions, beta distributions with easily computable mean and standard deviation variance. Each of these distributions is often used to describe a specific shortened examples in real life. Say, normal distributions are very well model the stock prices or foreign exchange rates or something of the sort. Exponential distributions are used to characterize the time between successive arrivals of customers in a service system, such as a call center. All right, let's return back to the characteristics of forecast. Point forecasts are usually wrong, right? Why? This is because the demand could be a random variable. In the past few slides, we have been looking at how to describe demand distributions and how to characterize random variables. Using that information, a good forecast should be more than a single number. Forecast should include some distribution information, typically the mean and the standard deviation. It's also worth remembering that aggregate forecasts are usually more accurate, and accuracy of forecasts erode as we go further and further into the future. Therefore, long-term forecasts are less accurate than short-term forecasts. Finally, don't exclude known information in your forecasting process. Unless you have some good reason to do so, let's examine some subjective forecasting methods. First, composites. Composites are a way of aggregating forecasts that come from different locations or different people or different geographies. For example, there are sales composites. Sales composites are found by aggregation of sales personnel's estimates of demand. There's election polling composites. There are websites that aggregate polling data that put them together. There are customer surveys. Customers provide a subjective evaluation of different services or demand, and that's put together. There's a jury of executive opinion. Jury of executive opinion is to collect informative data from executives and put them together. Then finally, there is a Delphi method in which the individual opinions are compiled and reconsidered. And you compile and reconsider and repeat the process until a group consensus is hopefully reached. Today, the day I'm releasing this video, a great example of Delphi method is there's college football ranking. These 12 people have their own opinion. It's compiled, and they reconsider until a consensus is reached. And that's a Delphi method. We're going to focus on objective forecasting methods. How do we forecast objectively using past data? We can leverage on past data to come up with forecasts. And two primary methods that are used for forecasting are causal models and time series models. Causal models are explained through causal analysis, and that's exactly what regression is. Right? You have some x variables that you believe causes the y variable, changes in y variable. Right? Let's say D be the demand of the future outcome that you need to predict, and assume that there are n variables or n root causes that will influence the demand. A causal model is one in which the demand D is formulated as a function of those root causes. That's exactly what regression is. Now you can imagine these causal models are very intricate, and we spent some time in the marketing analytics. In this particular module, I will discuss mainly the time series based models. What is a time series method? A time series method is just a collection of past values of the variable that is being predicted. So if you want to predict the sales data, you want to look at the sales data in past period. In fact, it can be considered a very naive method. The goal is to isolate the patterns in the past data to come up with good predictions about the future using the past data. The past data might have some characteristics such as trend, seasonality, or cycles in the data, or just some randomness in your data. We use these patterns to come up with descriptive statistics, which are useful then in coming up with a prediction or a forecast, or a weather forecast, or a sales forecast. And that's what we'll do in next few sessions. Continuing in the same vein, we're going to discuss forecasting, leveraging on more historical data. In particular, I'm going to be looking at two methods. One is moving average method and exponential smoothing, which I'll cover in the advanced slide. This exponential, and I'm not sure if I will hold you accountable. We'll get to that. All right. In this session, we saw one of the fundamental problems in operations called the news vendor problem. I showed you the example of news vendor problem, in which you have to make an operational decision under uncertainty. We also saw an application of news vendor problem at a well-known magazine firm. I've emphasized the importance of making good decisions in the face of uncertainty. In this module, we have to guide you making better decisions. To make better decisions, first we need to be able to describe the uncertainty in the data we collect. We also need to use this data to forecast future events. These are very exciting concepts. Okay, see you in next video.